Hello, everyone. I'm going to do a little voice-over PowerPoint presentation. This will be the same as the normal PowerPoint presentations that I have with the embedded sound files. It'll be the same content, but many of you are having difficulty operating the sound files. They are a little bit tricky. That sort of technology by today's standards is a little bit antiquated. It's just the way sort of PowerPoint is. And I know it's very difficult to try to rewind, the sound file if you want to stop and pause and re-listen to it again. So what I'm doing is I'm going to be just voice-overing an entire presentation. This, you're seeing it right now, will be embedded in the course modules, right? They'll be, on top. There'll be an ancillary, auxiliary sort of PowerPoint presentation. And I'm going to be doing this for all the present PowerPoint presentations. I'll be moving through them one by one, replacing those to give it a little bit better way of sort of controlling things and hopefully a better learning experience for you. Okay, so I'm going to do a screen share now. And, today we're looking at science and its origins. So I'll go over this PowerPoint with you. All right, so we'll take it from the beginning. All right, so there we have our little science insignia at the top of our slide, but what we want to sort of get into is, is what is science? And I think the most important thing is really understand that it is a process, a way of thinking. It's not a result. It's not something we find out about the world. Science is a way of thinking that yields a way of conceiving reality and really the nature of reality. Really, what is it? It wheedles fact from actual fiction. Now, what we have to think about too is that the science is something we will really have to learn. And it's not being smart. It's not learning anything like that. It's learning how to question the world in a certain way that doesn't come naturally. And I'll tell you why. Human beings are really concerned about things that mean something to them, right? We're looking for things that mean or change or transform our way of thinking, and we're sort of honed in on that around us. And why not? Something that transforms our way of thinking, that makes us happier, or that enjoys with another community, provides social satisfaction, of course, the key things, in the real elements of our life. It doesn't mean that we're tapping into the absolute truth, right? Sometimes science yields results which aren't pleasing to the self or the community because it can actually go against the grain of what the community thinks, the social facts of what reality is built on, and get down to the actual reality, right? And sometimes these things can be a little disturbing and troubling and quite politically unsettling, as you can see in the world around you, right? But when you're trying to get at truth, which I think should be our goal, it's really what we should be after, right? The scientific sort of method. Right? And it's a very easy thing to do. What we're looking for are simply patterns. We're looking for patterns that occur in the world around us, or more simplified, in a more simplified way, we're looking for the cause of effects, right? Something happens, the effect, and we're looking for the cause of something. But the cause is something beyond the mere sort of gaze. So if I took something like an object like this, now watch me, you're watching my hand, and if I throw it, it goes across the room, you'll see this thing flying across the room. You say, that's an effect. What's the cause? Well, obviously you saw me throw it, so the cause is me throwing it, right? But now, if you didn't see me throwing it, and all of a sudden this thing goes flying across the room, you see, there's something you need to be able to figure out. Why is it moving across the room? Beyond our mere gaze. Now we're starting to do science. We're looking for an explanation for this. Now, what we do is we first try to posit an explanation of why we think something happened, right, what the cause of it was. And when we do that, if we have a way of testing it, if it's a testable thing, we have ourselves a scientific hypothesis, a hypothesis. Okay? So I take a particular cause. I think I know what the cause is. I think I have a way of testing it. I employ that testing. That's my hypothesis. And I simply are trying to prove my hypothesis or disprove it or refute it. And if I refute it, then I come up with another hypothesis and retest until I actually find the cause or mechanism. And in nature, we're doing the same thing. And then we can look for patterns of things that happen in nature, or just simple cause and effect relationships with one thing we might happen to see. Now, the film Why Are We Here really delves into that. In fact, that entire film is about pattern and cause and effect relationships. And if you watch it, while Brian Cox during the film is finding a lot of interesting things, really the point of that film is to demonstrate the process of science and what it can actually achieve. Right. Okay, so we've gone through this idea of hypothesis, but I'm putting it into a little bit better focus that there's a hypothesis, and then there's really strong hypotheses that work their way towards theory level, right? So we're talking about moving from a hypothesis, like I can prove my hypothesis of what I think the cause of an effect was. If I can try to continue to do something which is quite counterintuitive, which is trying to prove what I've done is wrong, prove that what hypothesis is not correct, try to falsify it. And if I keep trying to falsify it, it keeps to resist falsification, my hypothesis can really elevate in towards theory sort of level. something that I can try to falsify my hypothesis under all conditions everywhere, all the exceptions where something, a cause and effect relationship holds together under a lot of different circumstances. It rises to the level of theory because it can resist falsification. So a good hypothesis always has a way of falsifying it, right? The best. All right, so talk about the roots of modern science. Yeah, here's the thing: is that Greeks, Greco-Roman period, 1st century to 6th century AD is really accredited for it, but that's not the truth. The Greeks did very little work in science whatsoever. Now they built, big empires. They built wonderful cities, and it's simply because their particular belief system and the pantheon of gods they had were to get the favors from the gods, and the favors were only to be given if the gods would come down and they would speak to them in person. That's why they built these large statues, right, to go visit the gods, and the gods would come down and embody the statues, and you'd be next to them asking for favors. But the gods would only come down if and only if the cities were, and reminiscent of what they left behind, in their Olympus, their palace of the gods. Thus, the Greeks were busy dividing or inventing things like geometry, mathematics, so they can build super straight. They built great looking cities, but not for the purpose of science, right? So they continue living in their demon haunted, magic riven world. So science really wasn't part of it. Of course, their legacy, is of course the grandeur of the buildings, and I get that is sort of an amazing thing, but it really has nothing to do with science. Where science really does come from is the medieval Islamic world, the 7th to 13th century. It was a 5 to 650 to 700 year period, incredibly productive. And that period flourished, in the Middle East, particularly in the Persian empires, but it was lost. And it was reclaimed later by Europe. So I'll give you a little brief overview of how that happened. I think it's kind of a fascinating look at this so that we can value a little bit. And maybe, sort of handle our ethnocentrism. We have a lot of Western ethnocentrism around, like, the Western people have created the world around us. The rest of the world, put us in homage for, homage to us for what we've done, which is not necessarily true. I think history shows a little bit, a clearer focus on the reality of this, of some of the things that maybe that we shouldn't have done. So let's have a look at how science got started. So it's begun by the Persians. Now, Persians really means Arabic-speaking people and some Farsi-speaking peoples also. And the classic Persian Empire would be somewhere pretty much where Iraq is right now. The center of the area was Baghdad. That was the real city of all intellectual activity. But, for a radius of 1,000 miles in each direction, we had efflorescing societies. We hear about that in the Fertile Crescent, Mesopotamia. All of these areas are sort of areas that were in dominion by these Persian societies. And by and large, they were highly secular. Even with the rise of Islam in the 7th century, it really didn't change much. They had a strong anchor in the civilizations about secular state, the separation of church and state, and they did it very well. Unfortunately, we're not doing that very well. Even though they've learned their lesson is 7th century, my gosh, we haven't really learned the importance of those values, but they did. Now, this is not to say that the entirety of the Middle East is the same now, right? Many parts are, many parts aren't, because we're looking back at the ancient sort of empire. So we can't compare the ancient kingdoms to what they are right now in the modern world. Now, to a lesser degree, the Moors were in this too. These were part of the Persian civilizations. That culture began to expand, moved into southern Spain, started moving up through Spain. And of course, when they moved through Spain, they were doing quite well. They brought great technology, even some more sophisticated ways of doing things, and even medicines, even agriculture. And of course, as you're pushing in on the Christian sort of dominated world, this Christendom at this time, there's a lot of jealousies because of that. And also, as the Persian empires began to push into Turkey, began to borderline on the western part of the Holy Roman Empire, it also put a lot of pressure on the Western rulers because they felt inadequate, inferior to the people that they governed, simply because all around them were members of another religious, belief system and cultural system that appeared to be doing better than them. And of course, when you're going to remain allegiance by your people, you need to be able to demonstrate that you're doing better than the people next door. And this actually led to a great deal of jealousy. It culminated in the actual Crusades, which was really to eliminate the presence of these folks who are doing much better. And it ended up actually collapsing science for us. We'll look into that real briefly. I'll give you a little outline. Right. Well, one thing about the West, one thing we're good at, I think all cultures are too, are imagining things. Imagining like what the world was in the ancient times. And artists no less do this, but problem is that the art is done well. I mean, the picture is done well. It becomes an indelible master And, that becomes our portal, our viewing. And myths about the past begin to develop, right? And change the reality of the past. So I will look at this painting here by Raphael that was done roughly around 1510. This is, I mean, we're talking 1500 years after the collapse of the Greek states, and by the time Raphael actually was visiting some of these places, that where the Greeks were at, they were in absolute ruins, absolute, all we had were ruins left and very little written evidence whatsoever of the activities. There's a few manuscripts of books that were there, about some philosophies, but not about science. But what he did is he produced this magnificent painting, right? The School of Athens. Look at all the scholars in there, pontificating huge things around the world, bringing new revelations about the world, breathing in a new way of looking at life. Not necessarily true. Right? This is a lot more imagination than it was the actual reality. And this has sort of, developed the mythology that we've sort of inherited. And you can see that even in colleges and universities with the Greeks, and we have a fraternity system and sorority systems and the Greek names that we have everywhere, right? We, as much as academicians try to do, bring in truth throughout the century, we can't resist the sort of the mythologizing, like the George Washington myth that is sort of part of our cultural experience. All right, so, a couple of little examples. So this guy Thales was considered the first scientist. He's a father of science. He's a Greek guy. And, Thales, postulated things like this as one of his biggest things, that there's a big earthquake where he lived, in the Greek world. And he said, listen, don't worry. You folks might think the gods are down there warring and battling back and forth, and the massiveness of their bodies are causing the earth to do this. But he says, don't worry about it. It's really, there are underground water, right? So you hear the earthquakes, but there's oceans underneath the ground, oceans, and they're sloshing back and forth, right? And it's the oceans rocking back and forth. It's not like the god Poseidon's doing anything. Well, here's the thing: is that people think that this is the first, non-supernaturalistic sort of explanation of events in the world, which is not true. I've worked with a lot of what you call primitive people, that are live in a very strict, sort of supernatural sort of world, and they have tons of explanations which are not mystical, right? About how things happen, that don't deal with gods or myths or spirits. So we can't throw that on. We can't throw that. That's the only alternatives the Greeks ever had. And this is the first sort of point of science, the very first person who thought a naturalistic sort of explanation. Now, next, we have to think about what type of explanation was it? Was it a hypothesis? No, because it's not testable. If he said there's an underground ocean, we have to have some evidence for it, right? You have to way of testing it. So what he was making is some assumption, which was entirely false. There is no giant underground ocean doing anything like this. He had no way of testing it. He never did test it, never did validate it. So when you're looking at something like that, it wasn't even a wrong guess. It's how a mythology is started. If you really understand what's happening here, you realize it's a false start. That this guy can't possibly be the father of science to Western world. It's not science whatsoever. Leucippus is another guy. Leucippus is a great guy. Another Greek guy lived in the 5th century. He walked around his home city and he waving his hands in the air. I guess it's kind of weird today, he's waving his hands. Hey, people, do you feel the things moving between your fingers? That's the air. They call this the ether, the air. I know what that's made of. It's made up of tiny little things, just tiny little things. There's lots of these tiny little things. I don't know how tiny they are. I don't know what they look like, but I just know there's tiny little things in there, right? And I'm going to call these tiny little things atoms. Okay, all right, let's think about it. Did he ever see an atom? Was there a way of testing it's made of smaller things? Or did he make an assumption? He made an assumption, right? Now later, in the 20th century, and it wasn't probably in the 1950s or 60s until we actually get electron, microscopy and like things that sort of verify sort of the nature of what's happening, that we get to see small things, right? And when these small things, what we do is we take the Greek name that Leucippus came up with, the atom, and we attach it to that as if Leucippus was the one who discovered them back in the 5th century, extending science back in time, right? That's not how it works. That's a logical fallacy. It doesn't work that way. So it's that sort of thinking that creates the mythology that strings this whole thing called science back in time. And it's not true. It's not true whatsoever. The poor Greeks, they lived in a demon-haunted, magic-ridden world like most cultures did, up into the real true sort of, emergence of science. And it's just the way it is. They're no greater or no lesser than the other civilization that's ever existed. They're just different in their own and very unique to study to on their own, but certainly not the harbinger or the efflorescence where science ever came from. Oh, even the greatest philosophers made a lot of mistakes. And this kind of illustrates the type of society they lived in. When people get into this, start realizing the Greeks, ooh, they're kind of schmucks in a certain way, and they lived very similar to how we do, at least politically, because they're human beings. You know, one of the greater philosophers of their time, arguably the greatest, next to Plato, and it was doing here Aristotle. You know, Aristotle was actually quite an imposing person, very large. And in that society, if you were large, big, muscular, and you look good, he did look good, you were like godlike. That's the way it was. And if you were godlike, you could think godlike things. So if you just pontificated and things came out of your head which sounded rational, they must be the truth. And this was Aristotle's sort of world. This is Socratic method. You just keep thinking about it and keep reasoning through it. It must be true. They never tested anything. And how about this? You know, he said that human males, had more teeth in their mouth than females. He wrote it in a book. It's not true. If normal people would have 32 teeth, 16 on top, 16 on the bottom, whether you're male or you're female. And you know, he just looked at people's heads and goes, there's no way to count. The male's head's bigger. It's just naturally so. And no one really ever said anything against him because he was rich and he was powerful. See how politics works? You know, whoever's the richest and the powerful and the most cast the most fear, people that sort of jump online with them like cronies is sort of what we see in many political parties that have happened, you know, last year, right? The cronies just sort of jump in, depending on how much noise is being made around it versus what the actual truth is, right? You get big lies circulating, okay? Now, next thing he said too is that heavier objects fall faster than lighter ones. Try it sometime. You know, get a small pebble and get a big rock and drop them exactly together, and you'll find out they hit the ground exactly at the same time. Right? It's the law of gravity. It's an inflexible law. How can you come up with something like this? So I hope you kind of see that they're not utilizing scientific methods or principles. I don't want to belabor this. I love ridiculing Greeks. I love ridiculing every society because I think it's really fun to see the fallacies of the past so that we don't make those same mistakes in the future. I don't care what past culture, you know, it is. Okay. You know, other things that that Aristotle had go wrong. You can see what's happening here on the slide. You can pause it and read. You know, just another thing is, you know, bringing this other example, and it's not going to help you understand it anymore, but you understand who the Greeks were. All right. Now, what we want to think about, and getting right back to science itself, is really when we're talking about, you know, looking for cause and effect relationships. What science does, though, is not just look for any cause and effect relationship. If we see something really complicated, you know, the end effect, let's say like the birth of the universe, like the Big Bang, boom, right? That's the end effect. That's the effect of something. The cause is usually pretty darn complicated. So what we have to do is find out what are the numerous subcauses, the smallest little things leading up to a major cause. There's a hierarchy of things. So we're trying to get to the simplest little thing. Science is a very humble pursuit. We start with very small things, very small things, and each one interlocks, and we build on the knowledge which we have so we can get a better grasp on how bigger, more complicated patterns are occurring. What are the causes about them? So that's called induction when we do that. We go into very specific things to very general things, okay? We discern patterns from looking at tiny little things. We try to look at bigger and bigger patterns and keep building on, right? So we work with induction. That's the way we build what we call grounded theories, right? Grounded from the bottom up. We haven't made a mistake to the bottom. Everything, you know, that whatever our big theory is supported by everything on the bottom, which we know is true, okay? Now, eventually, once you get a lot of things built together, all the building blocks, you can start making some bigger leaps in your thinking. Like, I think that big pattern over there is caused by this because all the underlying things that we've discovered supports me making that, right? That high level hypothesis. When we do that, now we're starting to be deductive, okay? We can move from like one theoretical position to another one by doing deduction, okay? And then once we started to do something has happened, we go back to try to prove it, back to induction again. We start building on building small building blocks again, another framework of knowledge, and then we try to do another big leap, another big deductive leap. So essentially, we're going from induction to deduction, induction to deduction, induction to deduction. You know, and we do that in all the sciences. I don't care if we're looking at, you know, physics, or chemistry, anthropology, right? When we're exploring the past and evolution, we're doing that all the time. So this is a common sort of thread. So for all science, we operate exactly, in the same premises, and we'll be doing that, and we'll see how that actually worked out for Charles Darwin, and how he elucidates his theory of natural selection. All right. So this is just giving you, how the, induction and induction actually works. You can go back and look at this, but I've basically given you sort of the, the overall sort of approach to it. Normally, again, we start with deduction, see a pattern, to the hypothesis, it moves to a theory, okay? And then once we have a big theory, it can generate other knowledge, other sort of hypotheses. They move to observation and confirmations, and theories can move to other hypotheses, other theories, right? So again, it's induction to deduction, induction to induction, induction to deduction, induction to deduction. I got ahead of myself there. All right. So, it's sort of very simple again. You see the wheel spinning here. We start with the prediction or a hypothesis, to the experiment, to the observation, to the theory. So we're starting with the prediction, which is the induction, right? Then we put everything together and we move to the theory level. Then we start doing deduction and start building greater sort of knowledge. Once we have a platform, it gets bigger and bigger and bigger and bigger and bigger. And that's really what we've done in science for the last couple of 100 years to build our sort of way in which we see reality. All right. Okay, so I've got other sort of examples of the Greeks. And I mentioned that, a lot of these folks, in the Greek society, they did some wonderful things, wonderful builders. My gosh, I have to say that they were great. I mean, some of the arts they produce, were actually fabulous too. But the mathematics they produce, remember, isn't science. Math isn't science. So I hope you understand that, math will receive results, right? We can get measurements, but unless you employ a scientific method and our experimental circumstances, you're not going to yield anything, because math is just a tool of science. It's just another tool. Okay. So there's no mathematical hypothesis. There's postulates that we make, but there's no hypothesis about the real world around us. We have to apply math in a certain way. Math on its own is a very abstract sort of thing to do, because there's no such thing as a mathematical hypothesis or experiment. It's simply the way that it actually is. Okay? All right, so I'm not going to move so much, talk a little bit about Archimedes here, just to save you a little bit of time. He's another one of these guys that we're talking about, in the early Greco-Roman world, about maybe how to sort of, use the concepts of mathematics, maybe to sort of investigate, the universe, investigate, where, Earth might be. And they were trying to measure things, to sort of see what might drop out of these measurements, right? But they didn't go in with a strong hypothesis, like, I think this is occurring, I see the pattern. So I'm going to arrange an experiment, okay, that yields data, that shows something. And then I can take the mathematics and apply mathematics to the data and see if this actually demonstrates the pattern I'm looking for. The Greeks never really made that connection, and that was really their sort of shortfall. They never knew how to really, take mathematics and integrate it very well. They were coming very close, but that's not what they hit. They fell a little short with this. The ones who really did it, again, with the Persians. And the casting character is surely, it's pretty extensive. When you're talking about, 500 or 600 years of people, living in a civilization, there's thousands of people. These are the notable ones, the ones that are very noteworthy, I guess. Al-Khwarizmi, a very, very interesting guy, who was an astronomer, a geographer, and he just developed algebra. So this is an Arabic term, al-shibra. People don't realize that algebra. And like the numerals in which you use to count, those are Arabic numerals. They're not English numerals or Latin numerals. They are Arabic numerals. That is the basis, how mathematics is really used, in the past, or the early civilizations, and what they were doing with these mathematics at that time is they were trying to find patterns in nature, right? Measuring things, seeing if patterns were there. And they began to see some sort of regular patterns in the stars above them, the patterns in which they're moving in the skies, circulating. But the issue that stopped them was they didn't know what the objects were themselves, right? It's one thing to see things move, but you got to get to the nature of what those things are to begin with. You got to move to the simplest. And they started way too high. These early guys are way up in the deductive, right, range without getting right down to the inductive range. But they did set a stage, like very much like the Greeks were doing in an earlier period, by developing the instruments, the tools to help them, sift through the data and make some sense out of it. Once they can try to mathematically model, right, the data to the pattern in which they're seeing. Okay? So he started to think about it. This guy named Avicenna started thinking about it. He took the tools of Al-Khwarizmi. And he said, okay, here's the deal. Let's take it down to the simplest thing. We're looking at the heavens above us, right? What are they to begin with? Before we can figure out what we are or what's moving, what are they? And they're points of light. They're points of light. So he was trying to figure out, Avicenna, like, well, if they're points of light, and light is on Earth, we can see light around us. Does light travel? In what direction does it travel? Does it scatter and go everywhere? Because when you look up at the heavens, you're going to see a star, it's twinkling, and it seems like light's coming out from all directions. Now, if light's coming out in all directions, and it's moving in a straight line, that means the object is spherical, right? So these are spheres around things in the heavens. Now, if light can be demonstrated that it doesn't move in straight lines. Maybe it moves in scribble lines, or there's an erratic effect. When you see stars twinkle, you have no idea what's happening with the light. Then you can't make any sense about it. But you need to know what the nature of this is, and that's the only thing in which you see. Okay. So he said, yes, we need to start moving for more basics. That's the thing. All right. So he put that sort of thought about it. Well, what happened is that at this time, a guy by the name of he came along and he said, okay, all right, building on everything I see in the past. He developed trigonometry. This is the basis of all calculus, right? And with trigonometry, you can do a lot more than you can with this algebra. But if you apply algebra and trigonometry together, you can get relative rates and distances, how things are moving in relation to each other speed-wise, and how things are changing in relationship to each other. So he begins to sort of devise a celestial model of the heavens, the mechanics. He puts everything together and can demonstrate how things are moving and make very good predictions of where things are coming up. Stars are coming up, where they're setting, and basically showing where the Earth is going to be sitting in relationship to the sun in the seasons, right? You can predict what season we are by looking at the distance between stars and the relative rates around us. So he's developing a fairly sophisticated model of the universe at this time, right? But at the same time, whatever those objects are out there, we know that we have to get down to light first. So he sort of misses, the idea of what we should be doing, on the local point, right? The guy who really did it was a guy who came around just even a little bit sooner than Al-Tusi, the same time as Avicenna. This is the guy I want you to remember. This is the guy right here, Ibn al-Hazm. This guy was awesome. He was just a practical guy. He said, okay, I get it. We have all these problems about celestial mechanics. We're going to figure out where the Earth is. Does the sun move around the Earth? The Earth move around the sun? And, is the Earth the same as those things out there? Because that sun seems like it's awfully hot to us, and I don't think the Earth is doing that. Now, all those other points of light out there, just like our sun, are just like the Earth. He needed to know. And he said, well, what we got to do first is we're going to go back and think about the idea of light. What is it? How does it travel? We're going to start with induction, the simplest thing. And then we'll build on what we know. All we got are points of light. So he takes a bunch of tents, lines his tents up, perpendicular to the sun, where it comes up, in the morning over the horizon, right? And he cuts little holes in the tents, one side, the next side, all at the same height. And the next tent, through the tent, the edges of the tent, the same height above the ground, same round hole, same size, all the way through about 6 tents. And on the inside of the last tent, he put a little target with the same size holes, entrance hole. So he said, okay, so if the sun comes up and the light's going through there, if it goes through the holes without diffracting, all over the tent surfaces everywhere, if it just goes through, and leaves everything dark here, goes through and just strikes the target on the last tent, the very bottom, and leaves the same size radius hole as the entrance hole without diffracting, it says at least the sunlight travels in a straight line. So you ran this experiment, but bam, it did. The light went in a straight line. It didn't diffract. All right. They said, okay, well, now that we have this sort of like sunlight, Does sunlight, does all light do this? So we started like, making little makeshift like torches and lanterns. He even did it with starlight on certain nights. It was campfire lights, every kind of light he could find, and place it perpendicular to the tent and ran the same experiment and find out, yes, light would travel, in that same straight line. We made a general principle that it seems no matter what, all light travels in a straight line. See, by testing all the different lights, he moved from that one induction, kept expanding it to all the different forms of light he could find to build something general, right? A general theory that light moves in a straight line. He started with simple induction, asking very simple questions, testing it, looking at the results, building a theory about light. And thus they could tell that those objects upstairs, up in the heavens, are generally probably round, right? So we're looking at orbital things. Absolutely, we learned something about the universe. Now we can ask bigger questions. So that's what science does. And Al-Hazen really, started to do this for the very first time. So, and there's one thing, I hate to ridicule Aristotle so much, but, he's known for being a philosopher, but a philosopher of what? I mean, you can get to be so good at throwing language around that people get really confused, and it just seems like it makes sense, but it doesn't at all. So if you ask, this is an exact translation in the English from Greek, or from book to the Enema. This is what he said about light. I'll read it to you. We have now explained what the transparent is and what light is. Light is neither fire nor any kind of whatsoever of body, nor an effluent, an efflux from any kind of body. If it were, it would again be itself a kind of body. It is the presence of fire or something resembling fire in what is transparent. What is that? It is certainly not a body, for two bodies cannot be present in the same place. Duh. The opposite of light is darkness. Yeah. Darkness is the absence from what is transparent of the corresponding positive state above. Characteristically, therefore, light is just the presence of that. Now you understand what a political speech is all about, because that's what he didn't say anything about the nature of light whatsoever, because they didn't have means of testing it. They didn't understand the scientific method. All right, so I don't want to go into this. You can see this in the Greeks thought that Aphrodite, the Greek goddess, had put little disciples in people's eyes when they were born, and they were all holding torches, and that's how you could see light. Light didn't come from that world around you. It was blasted out of your own light, of your own eyes, and it was a reflection back to you. And that's really what it was, right? Which is kind of silly. And of course, the Persians, the early Persians empires were looking in people's eyes, looking what the Greeks said, and said, actually, for us, we don't see anybody holding a torch in there. So with the absence of being able to see, that is what you call horsepucky, right? And it kind of showed you what sort of mythologies will sort of lead you to think. And that's fine, if you're not trying to get to the nature of truth. Thinking that there's a little disciple of Aphrodite in your eye is kind of entertaining, but it won't get you far, if you're trying to discover something real about the world. Now, the last thing I want to mention here about Al-Hazen, the most important, I think this is the most important thing ever. It's one thing doing science, and it's one thing trying to get at the truth, because who's doing science is humans, right? And boy, is there anything as treacherous as a human, right? Who hasn't been taught ethics and what real ethics are. And science only works when we have strong ethics. We have to verify our results. We can't fudge things. Well, look what Al-Hazen said. Now, ladies, I'm sorry, but this is a direct translation. The gender terms then were a little bit different. I wish I could just, use a different sort of pronoun, but place, women or whatever, every sort of blend of gender or whatever sexuality out there, because it's inclusive of all of us, right? So the word man is inclusive of all of us at this point. Okay? The duty of the man who investigates the writing of science, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. Okay? We do that in science. And that even means when somebody else comes up with a hypothesis, it's their duty to write it down, to write what they've done, what their hypothesis is, how they tested it, what materials, what methods they used, exactly what data they had, how they transformed and manipulated that data, and what that data says. Does it conclude? Does it refute? In a discussion, in a results and discussion area. And what we do as scientists, we read other people's data and we challenge it. We try to reproduce their experiments to make sure they got it right. Because we're trying to reproduce knowledge for humanity, to make sure there's no mistake. So when people challenge my hypothesis, I don't get offended whatsoever. I'm like, yeah, try to take it down, see what you can do with it. I hope I don't know if I'm right or if I'm wrong. I don't hope one way or the other. That's just what my findings are. So make sure you can reproduce them. So you see, now we can get at a point where we can always get to the truth that way when we are completely open and transparent. Next is very important. I'm going to say she or anybody should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency. I think that's so critical. So, think about it is if you're doing science yourself and there's some ulterior motives, you're like, so you're working for a big pharmaceutical company. And if you don't find something today, maybe you're not going to get a project anymore. Maybe everybody in the lab's going to get fired, right? So are you under pressure to fudge your results? You might be. And if you are, it's your duty to say, I can't do this. I have to not. I'm too involved in this, right? I'm too prejudiced against what I'm doing, right? I'm biased against it. You must let go of it. In the same way, sometimes people fall in love with their own ideas. Don't you all the time? You have an idea about the world. You think it must be true because you came up with it. It's my brainchild. It must be true. So why test it? Then if you get like that, you don't rigorously test, your own ideas out that way. You need to remove yourself from it and turn it over to somebody else. And Al-Hazim was so right. If you just do science with that sort of spirit we have in front of us, you're always going to get real good results and learn something about the world around us. All right, now, next thing I want to say is we lost science. It was being, distributed to the world, and it started being unleashed from the Middle East. Al-Hazim hit it right on the head. And of course, that was transforming Islamic empire. It was making their life great. That's what science does. Look at all the stuff you have around you. I mean, everything I've got here, remote controls, all this stuff you call high technology, your phones and stuff. It's not just high technology. That's the product of science. We don't think about it. High technology is science. Everything, as far as your eye can see, is a product of science. The way in which you live, if not, you would be living, in pretty much horticultural sort of societies with sort of, traction animals, and probably in a feudal society where your average age, if you're female, maybe 35 and male's 40, right? That's that world. That was the world before science. Now, as it begins to radiate through Europe, things are doing well. Again, as I mentioned earlier, there is a lot of jealousy that's happening, and the Holy Roman Empire, the Roman Church, begins to rebel against this stuff. It starts the Crusades to try to wipe out what's happening in the Middle East, hold them back. They kind of call them infidels, but they really weren't. They were just people who would develop more clever ways, right? Now, a lot of other things happen too, is that, there are other calls in the church. That science was bad because it distracted human beings from dwelling on the thing that they should be dwelling on 24 hours a day, and that's meditating on God, right? So if you see old, pictures, illuminations, there's always a person, and they're like this praying, and there's a big halo over their head. Those were like symbols. They were like to tell people they're not art. They used to hang them to remind people what you're supposed to do. Don't think about anything but God. Just pray all day. Don't think about why things happen. They just do. Raise your crops, kill your chickens, hand over your money, trim the tits, and that's all you got to do. Okay. So, this is another way people were trying to sort of keep science out too, because it would actually rival, the authority around the regime that had created the political regime, right? All right. So, the cleansing and the wholeness of the Christian empire, the simplicity of keeping science out was the top thing. And that actually meant going into the Crusades and actually defeating, right, and plundering and ending the great Persian empires. Right? So by the 11th and 12th centuries, it was almost all complete. And at this particular period of time, as these Islamic empires were under attack from Christians, another force was emerging from the Far East. That Genghis Khan, he really realized what was happening, and he flanked him. He came from the east and just brought the rest of the Islamic civilizations down. He really conquered them and just really destroyed everything. And then, of course, we have Mongol marauders came in, all the way for another century, just pillaging. Every time they would try to rebuild again, the Mongols would come in and destroy and just take all the valuables and riches, and to where they couldn't get on their feet again, and literally just destroy the empire. And literally everything was lost. And civilizations were burned. Many of the books that they had were gone. Most of the books that they had were gone. And that really marked the age of this wonderful thing we call the Islamic Golden Age, And it really culminated in 1258. That was the year that Baghdad, the intellectual center of Baghdad, right? It was almost completely destroyed. Interesting what we did in the 1990s to Baghdad too, what the United States did, right? Remember the war where there were really weapons of mass destruction in which they were not found? So in another way, we were very much, sort of like the Crusaders. I think we were the modern Crusaders on a mission to sort of do the same sort of things. Well, the thing about it is we have a lot of evidence of what's going on. We have, these tapestries, these, highly advanced sort of Islamic soldiers carrying weapons, but are far more advanced than what was in Europe at the time. This is a depiction here of Moors in Iberia. And so we know what was going on. We know about the bitter feuds and actual rivalries that were sort of occurring in the area, which sort of engendered the Crusades, and which saw the actual rapid decline of the Islamic Empire. Here's also talks a little bit about how the Moors, the Islamic people, were pushed out of even Spain. You can see the timelines here of actually what was going on through time. I show, year after year, they're pushing them away because, really out of sight, out of mind. And therefore you can go to the old political hierarchy stays actually in power. All right, enough for this. Now, what I do want to think about is how science, was actually reclaimed. That's the most important part about this whole thing. We know that we lost it by about 1278, 1300, with the final end of the Islamic Golden Age, and most of those books were destroyed. We had to figure out, how science was actually reinvented and who did it. So that's what I'll be doing with the next slideshow. So I'm going to actually end this one here right now. Okay. All right, guys, I'll see you on the next slideshow.